The end goal when we analyze the motion of a physical body is to obtain its displacement, velocity, and acceleration in terms of time. Displacement x, velocity v, acceleration a, knowing that the velocity is the rate of change of displacement and acceleration is the rate of change of velocity. We're going to analyze 4 different kinds of motion in this video. The first one being uniform velocity. Uniform velocity means that the velocity is always the same, and this happens when a body has an initial velocity in a certain direction, okay, we are in one dimension here, and that the acceleration is 0. Okay, acceleration is a velocity changer, so of course if acceleration is 0, the initial velocity will just stay the same the whole time. This happens, for instance, to a car cruising on the highway at constant speed. So uniform acceleration, we are in 1D as well, and as its name indicates, it's simply when we have a constant acceleration in a certain direction. And for example, this happens with free-falling bodies, which are experiencing an acceleration due to gravity. Then we have projectile motion that gets interesting. This is when you have uniform velocity in a certain direction, let's say in the x direction, and you have uniform acceleration in the other direction, let's say in the y direction. And that gives you trajectories that look like this. And this happens, for instance, when you throw a basketball. Then finally, we're going to explore uniform circular motion, which is when you have an acceleration which is constantly directed towards the center of a circle, and a velocity which is perpendicular to that acceleration. And when you have this, well, you have a motion a trajectory that looks like a circle like this around the center towards which the acceleration is always directed. And this happens, for example, to the trajectory of planets like the moon. Okay, it's a simplified version of the elliptical trajectory. When we simplify the model, it's close to a circle. Okay, let's move on with the analysis. Before digging into some examples, let's have in mind an overall strategy of how we analyze motion. The end question we're trying to answer is how is the body moving? So it's giving its displacement in terms of time, right? This is a direct answer to that question. But to obtain displacement, we have to know how displacement is changing, what is causing the displacement in the first place. And this is velocity. Velocity is what changes displacement. So if we have the initial displacement and we know how velocity in terms of time, so how this displacement is changing, well, we can deduce displacement. And how can we obtain the equation for velocity? Well, we have to know what changes velocity, and that's acceleration. And what is the root cause of acceleration? Well, it's forces, and we need to do some computation and find the sum of all the forces, so the net force acting on the body. And we know, according to Newton's second law, that this is equal to mass times acceleration. So with an analysis of all the forces acting on a body, we can deduce acceleration. And therefore, that takes us to the first step of any analysis, which is to analyze the root cause of motion, which is a free body diagram of all forces acting on the body. Let's look at a first example of uniform velocity, a car cruising on a highway at a constant speed of, let's say, 110 kilometers per hour. How would you represent the free body diagram of such a body? And here's the answer. The car feels its own weight equals to mass times gravity. There's a normal force that balances out weight, okay, the normal force which is applied on the tires to support the car on the ground. Then the car has a certain thrust that the driver is pushing on the accelerator, so to give some thrust to the car and to fight against drag in order to maintain his speed. Otherwise, he would slow down. And this is how constant speed is maintained. So any velocity that the car had in the rightward direction, for example here, well, it will be maintained all throughout. And this is how this car is maintaining a velocity of 110 kilometers per hour. Okay, so knowing this, when we have all the forces balancing themselves out, we can conclude that the sum of the forces are equal to 0, which means therefore that acceleration is always equal to 0. So now we know that the AT graph, the acceleration versus time graph, will just be a constant graph that stays at 0. And then this means that velocity is not changing. So velocity is staying at 110 kilometers per hour the whole time. And if displacement was at 0 when I start observing the car, well, displacement is constantly growing. The car is getting further and further away from this point of reference at a constant rate, and the slope of this line is actually the velocity. This is the constant velocity of the car. Let's now discuss the example of you pushing a block on a floor. Here you have a block of a certain material with weight mg and therefore reaction force mg because we're on a horizontal surface. And let's say that you give it a little push here. Well, you're not moving the block away from its position yet, so you have this friction force that's preventing you from pushing it. So you push it harder and harder and harder, and at some point, the friction, you'll arrive at a limit friction that won't be able to hold it anymore, and boom, you'll bulge it out of its position. And my question is, what is this limit pushing force, this minimal pushing force that you need to apply for to overcome this friction force, which we call actually the static friction force. We'll see later what the dynamic friction force is. So how hard do I need to push this block to get it moving, and what factors does this minimal push depend on? So what do you think this minimal force depends on? Maybe you thought of mass, gravity, the area of contact between the block and the floor, the roughness of the contact between the two. Well, the first surprise is that the area of contact doesn't matter. You can have a very large area of contact or a small area of contact. Actually, this doesn't come into play to determine the minimum force you need to bulge the block out of its position. So what about mass and gravity? Well, in fact, the key here is the reaction force. And the reaction force usually depends on mass and gravity, but not all the time. It could also depend on an extra pushing force downward, okay, which would increase the reaction force. So in general, it's not really mass and gravity that you need to remember, but rather whatever the reaction force is. And then, of course, the roughness of contact has something to do. If the contact is perfectly smooth, you can imagine that you'll need barely any push to bulge it out of its position. However, it can be also very rough, and then you would need more force. So this is quantified by a quantity that's symbolized by the letter mu. So here we have mu s because we're talking about static friction. And this quantity is between 0 and 1. 0 meaning a perfectly smooth surface, and 1 meaning a perfectly rough surface. And this mu s is what we call coefficient of static friction. So now we have the fundamental factors, and we can express the minimal push you need to move this object from its position. And it's in fact equal to the product of mu s, the coefficient of static friction, and r, the reaction force. So if I have a roughness of 0.3, and a reaction force of, let's say, 20 newtons, which would correspond to having a mass of about 2 kilograms in this situation, well, it means that the limit pushing force is 6 newtons. I need to apply 6 newtons to this block to bulge it away from its position. And to conclude the key learning from this part of the video, well, when the pushing force is under mu s times r, so under this 6 newtons force, meaning that imagine you apply a force of 1, then 2, then 3 newton, as long as you're under this 6 newton force, well, the friction counterbalances the pushing force, so we're in the situation where the block stays at rest. You need to go slightly above this limit pushing force, so slightly above these 6 Newton force in this example, to get it out of its position. Let's continue with this example of pushing a block and see what happens when we get it moving. So imagine again that you're pushing this block, you're pushing it harder and harder and harder and harder, and boom, you get it out of its position. You actually reach this P limit, which we said was equal to mu s times r. And actually, if you're able to somehow measure this P limit, it's interesting because then it means you can calculate the coefficient of static friction, which is equal to this P limit divided by mg in this case, because r is equal to mg. So now once you bulge it out of this position, how much force do you need to keep it going? Actually, do you need as much force as this? Do you need to continue applying the same pushing force? Well, usually no, because friction is in such a way that, yes, at the beginning it's hard to get it out of its position, but once you got it out of its position, you need a smaller force to keep it going at constant velocity. So here you can get rid of this extra force you don't need anymore, and you have a smaller force, which we'll call PV, for the pushing force needed for constant velocity. And when you're at constant velocity, you know that all forces balance each other out according to Newton's first law. So you have a friction that's equal to this PV. And now we therefore need a new quantity, because it means that the roughness, the amount of roughness is not the same anymore once you're moving. So we don't have a coefficient of static friction anymore, but a coefficient of dynamic friction, which this time is equal to PV, the blue force here that I just came up with, divided by mg. All this friction stuff, in my view, was a great illustration of Newton's first law, which says that a body will stay at rest or keep moving with constant velocity unless acted upon by an unbalanced force. So as long as the forces are balanced, as long as friction is equal to the pushing force, that friction balances out the pushing force exactly, well, either we stay at rest, the yellow situation, or we keep moving at constant velocity, the blue situation. Here I took a situation with these numbers. Mu s is 0.3, coefficient of dynamic friction is 0.2, and mass is 2 kilograms, meaning that I would need a 6 Newton force to barely get the block moving, and a 4 Newton force, so smaller than the 6 Newton force, a 4 Newton force to keep it moving at constant velocity. And the equation to describe the motion of a body, which is in the context of Newton's first law, in the context of balanced forces, is x is equal to vt. Displacement is equal to velocity times time. And if we were to draw a displacement time graph, we would obtain a straight line, and the gradient of this straight line is the velocity. Let's continue pushing this block some more, but this time getting out of the situation of balanced forces. Now we're going to have an unbalanced force. So the question is, what if I push it with even more force? I give it an unbalanced force. What happens to the motion of the block? How can I characterize its acceleration, its velocity, and its displacement as functions of time? Okay, so let's go back to the situation where I was pushing the block at constant velocity. I reached a friction force of 4 newtons, which is the maximum dynamic friction force that I can have. So if I push it even stronger, I will unbalance this 4 Newton force. And let's say I apply an 8 Newton force instead of this PV force. Well, I create an unbalanced force of 8 minus 4, which is equal to 4 newtons. So now that we have an unbalanced force, let's apply Newton's second law, which says that the unbalanced force is equal, generates an acceleration, and there's an equivalence, which is unbalanced force is equal to mass times acceleration. So if I divide by math on both sides, I obtain that acceleration is the unbalanced force divided by mass. In this case, 4 newtons divided by 2 kilograms. So I obtain 2 newtons per kilograms, also known as 2 meters per second squared. So we have a constant acceleration of 2 meters per second squared, and this is why in this situation we talk about uniform acceleration. And if we had to draw the AT graph, it would be a straight line, in this case with an acceleration of 2. Okay, so from then, how do we find the velocity? Well, we know that delta V is equal to A times delta T. Okay, this means that V is the gradient of that A is the gradient of the VT graph. So we have here a constant gradient, so we have a straight line, and that has equation v is equal to at, where at is the gradient. So here, in this case, since a is equal to 2, we have a straight line going through the origin with gradient 2. Another way to see it is that we could have taken any t here, so this yellow time, and since delta v equals a delta t, it means that v is the area under the at graph. Here we have v for this certain time. So v is the area of that rectangle of side a, the constant acceleration, and t. A rectangle of sides a and t, its area is simply a times t. So now that we figured out the graph for the velocity, we can figure out the graph for the displacement. And we know that we have a similar exercise to do here, where we'll have to take the integral of the velocity in calculus jargon. And we have delta x is equal to v delta t, meaning that if I take any t here, this purple t, and I want to obtain the displacement when I have the velocity time graph, well, I need the area under this line. This is the integral of velocity until time t, and the height of this triangle is at. The width is t, so the area of that shape is 1/2 of at squared. So I have a parabola that looks like this, and that has an equation 1/2 of at squared. Finally, if we plug in the values, we obtain that a is constant at 2 meters per second squared, v is a linear function of time, where v is equal to 2t in this specific example, and x is a square function of time, where we have x is equal to t squared in this example. And this is very typical of uniform acceleration, constant acceleration, a linear velocity, and a square displacement. So now let's analyze free fall, which is a very classical example of uniform acceleration, and I suggest you pause the video and try to come up yourself with what the AT, VT, and YT graph will be, knowing that Y is in the displacement in the downward direction. Okay, so here's the answer. First, you need to find the sum of the forces acting on the body, so the total unbalanced force. Well, here we have only one force acting on the body, so the unbalanced force is simply the weight, which is equal to mg. And we know from Newton's second law that the unbalanced force is equal to mass times the acceleration of the body. We cancel out the m's on both sides of this equation, and we obtain the fact that A is constant and is equal to the strength of the gravitational field, G. So we have a straight line for the AT graph. We take the integral of G, we obtain GT. So we have V is equal to GT, a straight line going through the origin with gradient G. And finally, for the YT graph, we take the integral of GT, and that's 1/2 of GT squared. And we obtain the following parabola with the equation Y is equal to 1/2 of GT squared. And that's it for free fall. Now let's think about something trickier. A person is throwing a ball upward, and I'm asking you to come up with the AT, VT, and YT graph in the situation where the initial speed given to the ball is an upward v0 velocity, and the y-axis, the displacement axis, is directed upward. So try to think about that, pause the video, and try to solve it on your own. Okay, so this problem is a bit trickier because it's not simply dropping a ball from rest, we're actually throwing it up. So there's a new parameter here that we have to take care of. But when you do the free body diagram, which is always the first step in analyzing any body in motion, well, you realize that the only force that's acting on this ball all along is its weight, and therefore the acceleration that acts on the ball is a downward G. And some students get confused about this because the ball is moving upward, so they're thinking, well, it should be an upward force acting on it to make it move upward. But that's not the case. There was an initial impulse that was given to the ball here, which helped it acquire this initial velocity of v0. But then all along its trip, there's only its downward weight acting on it. and therefore a downward acceleration g, which is first reducing the upward velocity until it gets to the top, then the velocity gets instantly 0 at the top, and then it starts accelerating it downward all the way until the floor. So all along we have an acceleration of minus g. Why minus g? Because we decided by convention here to direct, to choose positive to be the upward direction, as you can see here. So acceleration is minus g. I have this constant acceleration, so we're still in the case of uniform acceleration. Okay, I didn't change the chapter yet. And if acceleration is minus g, to obtain the velocity, I just need to integrate this function to find the area under the graph, and I find that v of t, v as a function of time, is minus gt plus v0. And here's the trick. If my initial velocity is an upward v0, then when I do v of 0, so setting t to be equal to 0, well, this term disappears, and I need v of 0 to be equal to v0. So this is an integration where I can't neglect the fact that I have a constant initially. So what kind of equation is that? Well, it's a linear function with intercept v0, so it starts here at v0, and then with a downward gradient of g. So we have something that looks like this. Not very well drawn. Let me take another try. Here we go. And we have a slope, a gradient of minus g. And we achieve here 0 velocity, and then the velocity becomes more and more negative, meaning that the motion is downward. That makes sense, right? So we start with a positive velocity, which gets closer and closer and closer to 0. And at some point we reach the top of the trajectory, and then the ball starts going downward with faster and faster speed, like in the situation of free fall. And that's the VT graph that we obtained by deducing it from the AT graph. Now what about the YT graph? Well, here by integrating the function, the velocity function, we obtain first here minus 1/2 of gt squared, minus 1/2 of gt squared, plus v0t, and I don't need to add a constant because I set 0 to be the point at which the ball was released. So this is what the function looks like, and if we graph this yt function, let me set the axis here. This is when the ball was released, and we have a downward parabola, well, a bell-shaped parabola. Why? Because we have a negative factor here. That looks like this, and until I reach the floor here. Okay, noticing that the place where the ball was released is a bit above the floor. So here I have the floor, and here this is 0, the displacement 0, where the ball was released. Okay, and that bell-shaped parabola makes sense intuitively. We have something that moves up and up and up and up, then it starts moving down and down and down and down until it reaches the floor. Can we characterize now this height h, which is the maximum height that the ball will reach, depending on the v0 velocity? Well, this maximum point is reached when the velocity reaches 0 here at time 0. So at time t0, I chose to call this variable this way. At time t0, I reach a velocity of 0 and therefore the maximum height. And this t0 is achieved when v is equal to 0. So when t is equal to minus v0 divided by minus gt, so t0 is equal to v0 divided by g. And if I replace this in the y equation, I obtain that y0, that I actually called h, this maximum height, h is equal to minus 1 over 2 g times v0 squared over g squared plus v0 times v0 over g. Therefore, obtaining minus 1/2 g divided by g squared. Here I have 1 simplifying, so I have minus 1/2 of v0 squared over g plus v0 squared over g, which gives me a result of 1/2 of v0 squared over g. Now imagine that I want to obtain the velocity vf, which is the velocity right before the ball touches the floor. Okay, so let's say that the floor is at a displacement that we'll call yf for displacement when I reach the floor. Okay, so this is yf here. And I want to find the velocity when the displacement is yf. Okay, what can I do for that? Well, I can use an equation that analyzes the system from an energetic point of view. That says that the kinetic energy that I have at the beginning plus the work done on the object is equal to the kinetic energy at the end. Let's call it final kinetic energy. So the kinetic energy at the beginning is 1/2 of mv0 squared. There's only one force doing the work here, and it's the weight, and the weight is a downward mg, so downward mg minus mg times the displacement. Okay, so here we have what expresses the gravitational potential energy doing work on the system, minus mgy. Okay, to obtain finally 1/2 of mvf squared, and remember that vf is our final velocity when we reach the floor, and this is the variable we want to obtain in terms of everything else. Okay, so to isolate that variable, let's divide everything by m and multiply by 2. So divide by m, multiply by 2, divide by m, multiply by 2, and divide this by m and multiply it by 2. I obtain finally vf squared is equal to v0 squared minus 2gy, and here I know that the displacement is going to be some given data in the problem if I had to solve the problem, and it's this yf. Okay, I wanted to obtain vf in terms of yf, g, and v0. I have one more step left, which is taking the square root on both sides, and I finally obtain the velocity here on the floor in terms of the other variables of the system. Okay, to conclude on this ball throwing problem, what did I manage to do since the beginning? So I managed to obtain the AT, VT, and YT graphs with their equations here. Then I managed to obtain some characteristics of the trajectory, which is the maximum achieved height, this h in terms of v0 and g. And I also managed to obtain the speed that I achieved right before hitting the floor that I called VF, and I obtained this VF in terms of the initial velocity V0, G, and the displacement of the floor compared to the initial point of release of the ball. So now let's think about this rather famous problem of the inclined plane, and then we'll be done with uniform acceleration. I got it started for you here with this drawing, the beginning of the free body diagram of this inclined plane, where you have a plane that has an inclination of an angle theta, and the trick is to tilt the x-axis because we want to stay in one dimension, and here we know that the block is going to move down like this along the x-axis that I just designed. And to give you an indication, this angle is theta as well, because in this right triangle, this angle is the complementary of theta, and since this is a right angle as well, this is the complementary of theta, so we're back to theta. Okay, so here we have an angle of inclination of this arrow, that's this mg arrow, which is theta. We have a force r, and there's one missing, which is the friction force. Okay, so here we also have a little friction force. We have actually a block that's being accelerated downward, so we're in the case of dynamic friction force. We have something equal to mu d, coefficient of dynamic friction, times r. Okay, now knowing all this data, you're required to find the acceleration, velocity, and displacement functions in terms of time, knowing that this block was released from rest. To get this started, the first thing you need to notice to make this problem more practical is to decompose this force, which is neither in the vertical nor the horizontal direction. Okay, it's not in the direction of the axes. So this weight, you need to find its vertical and horizontal components, and then you'll see that it will be much easier to solve. So the horizontal component here, I'm projecting towards the angle, so I obtain mg cosine theta. So that's this component of the force, and this component of the force is therefore mg sine theta. Okay, so now I can just cross out this force because I decomposed it into its two vertical and horizontal components. So I'm left with an mg cosine theta and an r that compensate each other. So we have r is equal to mg cosine theta. And then an mg sine theta, we're told that the block is accelerating downward. So an mg sine theta, which is greater than this mu dr, which is, by the way, equal to mu d mg cosine theta, since r is equal to mg cosine theta. So now to look for the net force, the unbalanced force. How do I do this? Well, I know in the vertical direction that there's nothing interesting happening. The block is neither being accelerated upward nor downward into the floor, so r and mg cosine theta, we already said it, they compensate each other. So what we're interested in is in the x direction. In the x direction, the total force, the net effect, is mg sine theta in the positive x direction, to which I will subtract mu d mg cosine theta minus mu d mg cosine theta. Okay, so the force, I can factor mg out here. I have mg times sine theta minus mu d cosine theta. Very good. So knowing that the unbalanced force is equal to ma, I need to divide this unbalanced force by m to obtain the acceleration. Acceleration is equal to the net force divided by m, which is equal to g times sine theta minus mu d cosine theta. Cosine theta. Very good. So now I have acceleration in terms of time. Once more, I'm in the context of uniform acceleration, except that my acceleration depends on the angle of inclination, the gravity, and this coefficient of friction, which expresses the roughness between the two surfaces. Okay, and let's, to simplify things, let's call this constant acceleration A0. Okay, it's just a bit of a complex expression here, but we could just replace it by this letter A0. And then we just have a similar thing for the velocity compared to the previous examples, which is just integrating a constant. So I obtain A0t, and I released it from rest, so I don't have any initial velocity. And finally, I have an xt, which is equal to 1/2 of a0t squared. I just integrated the velocity equation. And that's it. That's for the inclined plane. And now for a summary of everything we learned in this video about uniform velocity and uniform acceleration. We could start again by just stating Newton's first two laws, which says that as long as the forces are balanced, the body continues being at rest or moving at constant speed, and as soon as I have an unbalanced force, then this unbalanced force causes the body to accelerate, and I can express the acceleration as this unbalanced force divided by m. Okay, and then I have an acceleration which is equal to some constant, which means that I'm in the case of uniform acceleration, and in the case of uniform velocity, it would just mean that a is equal to 0. Okay, and then all these equations would still be okay for uniform velocity. V would be equal to v0 and x v0t. But in the case of when I have an acceleration, I have these terms that are added, and I obtain, by integrating acceleration twice, the equation x versus t, which is equal to 1/2 of at0 squared plus v0t. And this is the famous equation for uniform acceleration. Then we saw that we could obtain another equation which expresses final velocity in terms of initial velocity, acceleration, and displacement, which is the following, and that we obtain by studying the system from an energetic point of view, saying that the initial kinetic energy plus the work done by the net force is equal to the final kinetic energy. And finally, we learned a great deal about friction, which is that we need a minimal pushing force to bulge the body out of its position, and that's equal to the coefficient of static friction times the reaction force. And if the body is moving, well, then we can calculate the friction, the dynamic friction force, by multiplying the coefficient of dynamic friction by the reaction force. And that's basically, in summary, everything we learned in this video.